We are the Electrical, Electronic, Telecommunicational Sectional Committee of IESL. Today, actually, we are pleased to host our second public lecture on acoustic imaging cameras for industrial condition monitoring. Now, in these sessions, we are actually focusing on gaining knowledge and insight from the expertise in overseas. So today is actually one of the first steps in that direction. So without much time, let's begin the session. So this session is actually having a presentation followed by a Q&A session. So you can raise your questions at the end of the session, and also you can raise your question in the chat box. So they will be addressed at the end of the session. So I would like to invite Chairperson Engineer Viraj Muthugala to welcome you all and also to introduce our resource person, Engineer Malla Malraj. Thank you.
Thank you, Dishanta. Thank you and good evening all. On behalf of Electrical, Electronics and Telecommunication Engineering Sectional Committee of ISL, I warmly welcome you all for today's webinar. Today's topic will be one of the interesting and kind of a new topic. It is acoustic imaging cameras for industrial condition monitoring. So today, I believe today's session will be a highly relevant topic. It covers one of the advanced technique for detecting partial discharges, gas leaks, and other kinds of mechanical faults. So it will be very much crucial to improve asset reliability and as well as predictive maintenance in modern industrial systems. So we are delighted to have as the resource person today, Engineer Malla Malraj. He's a technical specialist at FLIR Systems R&D, and he has over a decade of experience in the aspects of operation and maintenance in Lakija Power Plant. And at the same time, he has served as a project engineer during the Puttalam Coal Power Project in Phase 2. I believe with his extensive industrial and power plant experience, we will be having a fruitful session in today evening. So with that, I would like to thank for you all for joining today, and we will be having a productive and engaging session toward the evening. So with that, I would like to invite Engineer Malla to start the session. Thank you.
Thanks a lot, Engineer Viraj, for that nice introduction. And also thanks a lot for the IESL for inviting me for today's webinar. And good evening, all of my fellow engineers from Sri Lanka, and good afternoon, maybe good morning, the engineers and all the audience who are joining from all around the world. So let's directly jump into today's webinar, which is acoustic camera for industrial condition monitoring. Acoustic camera may be sometimes called ultrasound camera. So both the names are referring to the same device. Okay, so let's quickly go through the agenda. So first, we will briefly discuss ultrasound physics and then ultrasound detection methods, beamforming and ultrasound cameras, asset PF curve, and then applications of ultrasound cameras such as partial discharge, leak detection, mechanical fault detection, and then finally the post-processing and analytics tools. So at the end of the webinar, we can have this Q&A session. If there are questions, I am happy to answer as much as possible. Okay. So what is ultrasound? And what is audible sound? You know what is audible sound is? That is the mechanical wave that we can perceive as sounds. So those sound waves have certain characteristics, basically this frequency range, which is 20 Hertz to 20 kilohertz. So if the sound wave is fallen in between 20 Hertz and 20 kilohertz, we call them as audible frequencies. When we go for the lower frequency than the 20 Hertz, we call them infrasound. There are such animals, those who can hear this sound as well. But when we go beyond 20 kilohertz, we say ultrasound. That is the very high frequency sound. Of course, there are certain animals who can hear this sound, but as humans, our ears can't perceive this kind of high frequency sound. Okay, so there are two types of ultrasound. Of course, audible sound as well, based on the sound transmission path. So if we have a sound source, and from this source, sound can be transmitted, for example, to our ear or the microphone or whatever the detection device, either through the structure or through air. When this sound transmits through the structure, we call them structure-borne ultrasound. When the sound transmits through air, we call them as airborne ultrasound. So like this, we have these two types of ultrasound based on the transmission path. Okay, so as we have this kind of two types of ultrasound as structure-borne and the airborne, we can have two different types of detection. So when it comes to structure-borne ultrasound, we would need the contact sensor to detect this kind of ultrasound, because we want to measure this ultrasound on the device or the sound source itself, so that we have to plug or mount our sensor on the device itself. As an example, if you want to measure the ultrasound on the motor bearing, as the structure-borne ultrasound, you would need to mount your ultrasound sensor on the bearing housing. So since we are mounting our sensor directly on the sound source, those are immune to ambient noise. So it doesn't matter how much loud the ambient environment is, because we are directly measuring on the sound source itself. So it is more or less like we are measuring our vibration with our vibration meters. When we are measuring vibration on, for example, this kind of a bearing, we directly measure we directly mount our vibration sensor on the bearing housing. In the same way, we mount our contact sensor for the structure-borne ultrasound on the bearing housing. So the difference between measuring vibration and the measuring structure-borne ultrasound is that in the ultrasound we measure in very high frequency vibration, and the normal vibration we usually measure the low frequency. That's the only difference. Otherwise, technically both are the same. But when it comes to microphone or the airborne ultrasound, we need microphones. So in that case, we don't measure directly on the sound source. Instead, we measure the pressure waves which have been generated by the structure-borne or the sound source itself. So it will provide a safe alternative for measuring ultrasound. If you take, for an example, medium voltage switch gear, you can't put your contact sensor on each of the compartment. It is on one hand it is not safe, on the other hand it is not practical. So in that case, we can use airborne ultrasound to detect, for example, partial discharges. So we can do this kind of inspection in a safe distance with airborne ultrasound. So this is an example case of using airborne ultrasound. So this kind of device which used to detect airborne ultrasound is called ultrasound probe, which is normally a microphone. So it is nothing other than the microphone. So we can have this ultrasound microphone integrated into this device, and we can do this kind of scan over the areas or suspected areas to detect if there is a ultrasound source, for example, like a partial discharge. So how we detect or the perceive whether there is an ultrasound source or not. So as you can see in this picture itself as well, there is a sound pressure level measured in decibel. So based on the decibel level, we can guess if there is a strong ultrasound source presence or not. On the other hand, often with these devices, the manufacturers provide a headphone. Of course, we can't hear ultrasound, but this device can convert this ultrasound into lower frequencies so that users can hear. So based on this hearing perception, based on this the intensity of the sound, they can get a clue about whether there is a strong ultrasound presence, for example, inside this high voltage cabinet. So in that way, we can measure faults like partial discharge. So this is kind of a lightweight and portable device, and it is low cost alternative as well. Okay, so then we have kind of advanced airborne ultrasound equipment. It is called ultrasound cameras. So the difference between an ultrasound camera and ultrasound probe is that in ultrasound probe we have only one microphone, but in ultrasound camera we have number of microphones. For example, in this camera, in the picture, we have 124 number of microphones. So why do we need such a big number of microphones? Because if we have number of microphones, we can localize the sound source without hearing like we did in the ultrasound probe. So how does it happen? The principle is called beamforming. So this is the core principle of ultrasound cameras, the beamforming. What does really beamforming mean? So imagine there is a sound source over here in this location, and we have our number of microphones, so-called microphone array here. So from this sound source to different microphones, the distance is not a constant. So for example, if you take from this sound source to the nearest microphone, if there is a sound, it will reach faster than the other microphones. In other words, there is a delay for the other microphones compared to the this microphone. So based on this delay, we can this device can calculate from which direction the sound actually comes from. So this exercise can be done for different locations, and this camera can triangulate or locate the strongest sound source in the field of view. So that's how these ultrasound cameras locate the sound source without even hearing to the sound source by the user. On the other hand, since this microphone array has number of microphones, for example, 124 microphones, so they know this distance between each microphone relative to each microphone, so that it can negate this delay and adapt all these sound, so that it will get a beamformed signal that is having a high signal to noise ratio. So it would help to locate even tiny sounds, even a very faint sound in a loud noisy environments as well. So in that way, it can locate as well as it can increase the signal to noise ratio. So that's how these ultrasound cameras are being built. So this is the output of the ultrasound camera. So it gets the sound source location from the beamforming, and it overlays on the optical camera view. So when these cameras are being produced, this alignment is being done with the non-sound source. When this alignment is done, it can be used anywhere in the world to detect whatever the ultrasound source. So in this example, it is located in this partial discharge on this insulator, and this so-called heat map is being overlaid on the optical camera view. So users can quickly scan whatever the area they want and locate the ultrasound sources. That's the principle behind the operation of an ultrasound camera. So as I said, number of microphones would help to increase this resolution and the increase of sound signal to noise ratio. So when we double the number of microphones, we can approximately increase the signal to noise ratio by 3 decibels. Okay, so this is how does it look like an ultrasound camera. In this front view, you have this microphone array, and in the rear side, you will have this optical camera, which is being overlaid by this heat map or the sound localization map. So we have microphone array and optical camera, and inside we have this beamforming processor, which does all these calculations to localize the sound source. So as I said, this enables to inspect large areas very quickly, hassle-free inspection. It would provide a hassle-free inspection. For example, locating small leaks, partial discharges, or impulsive faults especially from a safe distance. Okay, so now we know what an ultrasound camera is. Then let's go to ultrasound camera applications one by one. So basically there are 3 types of applications that are commonly being used for this kind of ultrasound cameras. The first one is partial discharge detection, and then pressurized gas leak detection, and also mechanical fault detection. First of all, let's try to understand what does this asset PF curve mean. So it is important to understand this curve to get an idea why ultrasound inspection is actually needed. So in this curve, this x-axis is time and the y-axis is equipment health, the condition of the equipment. So at time t equals 0 at the beginning, let's assume that the equipment is being just installed and commissioned so that it is at its highest condition. So over time, there might be faults that might develop. So at this point, let's assume failure starts. And then after some time, so this curve shows how does its health or the condition deteriorate over time until the failure point. So during different time intervals, it will give symptoms so that the maintenance engineers or the technicians can detect this or assess the condition of the asset. So ultrasound is considered as the very first symptom or the measurable parameter that would emit from the failing asset. So first it will start to emit ultrasound, and after some time it will be appeared in the vibration spectrum, and after some time maybe in the oil particle analysis. After again then it would be monitored during wear and tear inspections, and then audible noise, and just before failure it would increase the temperature so that heat may be appeared, and finally failure. So you can see from this PF curve means here we have this potential failure and here we have failure. So that's what we call PF curve, and this PF curve ultrasound is considered as the first line of defense. That means if you do ultrasound inspections, that would provide the first line of defense so that we can identify potential fault at very early stage so that we would have considerable amount of time frame to act. So it is very much important to do this kind of ultrasound inspections in predictive maintenance to identify failure modes or the potential faults in earlier as much as possible. Okay, so let's go to the applications. The first application of this kind of ultrasound camera is the partial discharge detection, or we call PD. What is a partial discharge? So in high voltage systems, we have insulators. So in these insulators, there might be localized discharges or the localized breakdowns that might be caused by local increase in electric field stress. So these discharges would produce ultrasound. Other than there might be ultraviolet rays and other signals as well. But in our application, it would produce ultrasound that can be detected by using ultrasound cameras. So it is a known fact that partial discharges are responsible for like 80% of insulation failures in high voltage systems. So in failure of high voltage systems, the partial discharge would be the would account for the 80% of the failures. And if we consider these acoustic cameras as partial discharge detection, we can detect partial discharges by using acoustic cameras whenever there is an external PDs. So there might be internal PDs as well as external PDs on these insulators. So when it comes to external PDs, for example, corona discharges and surface discharges, it can be easily detected with ultrasound cameras. As an example, if you take air insulator switchgear or the outdoor high voltage switchgear, the most of these partial discharges are happening externally, either as corona or surface discharges. But on the other hand, if you take a transformer or GIS, those are kind of enclosed high voltage equipments, so that they would have internal partial discharges. So these internal partial discharges, of course, would generate ultrasound, but it would not emit into the external environment as an airborne ultrasound, so that it is not that much practical to detect this kind of partial discharges by using ultrasound cameras. Okay, so now we know what is partial discharge, and then let's jump into what kind of partial discharges are there. So there are different types of partial discharges. There are basically 5 types of partial discharges. First one is called negative corona. So whether it is negative or positive corona, the corona discharge is a discharge from high voltage conductor to atmosphere. So we know that this atmosphere has air, and air has a certain breakdown voltage depending on the humidity and the environmental factors. So normally it is around 30 kilovolts per centimeter. So whenever this local field stress exceeds this breakdown voltage, this partial discharge would happen to air. So those partial discharges are called corona discharges. So this corona can happen both during the positive half cycle as well as the negative half cycle of the AC waveform. So when it happens during the negative half cycle, we call them as negative corona. And when this corona discharge happens during the positive half cycle, we call them as positive corona. So usually negative corona is more stronger than the positive corona, because negative corona are caused by the electrons, which has very good mobility compared to the positive corona, which is being caused by these positive ions in the atmosphere. So those are having higher weight than the electrons, so that those positive corona would not have much mobility. So that positive corona is always having lower. I mean, if you take the strength, the negative corona would have a higher strength than the positive corona. Okay, so when it comes to internal PDs, so as I said earlier, internal PDs can happen whatever the internally, for example, inside the transformer or GIS, as well as inside an insulator as well. So as an example, if there is a void inside an insulator, that void might get exceed this breakdown voltage, so that partial discharge can happen. Usually those partial discharges are not being able to detect with these acoustic cameras, but both negative corona and positive corona can be easily detected with these acoustic cameras. And the next type is surface partial discharges. So as you can see in these two pictures, so it can happen along the surface of the high voltage insulators, most of the time because of the contamination of these high voltage insulators. So the contamination can happen due to dust, salt, together with moisture. So those should create localized partial discharges, and those can be easily detected with acoustic cameras because those are happening externally. So over time, these surface discharges might cause permanent damages, so-called surface tracking. So like in this picture, so you can see these carbonized paths. So those are called surface tracking. And if you don't take actions, even at this level, it might lead to complete flashover and the failure of the equipment. And finally, we are having these floating partial discharges. So floating means the partial discharge happens between two different voltage levels, for example, floating voltage. So as an example, in this case, there is this support insulator clamp, and through this high voltage conductor is going through. So in this case, these two conductive elements might have two different voltages, so that there might be tiny discharges that can happen between these two conductive parts. But this kind of things are not that much harmful, and it is a kind of a non-effect. But if there might be other types of floating partial discharges. For example, if there is not if your earth resistance is high, and some of the metallic surfaces might have elevated floating potential, so that there might be a discharges from high voltage potential to those floating potentials. That would indicate serious design failures. So those type of floating discharges always should be addressed timely. Okay, so we know that now we know there are different types of partial discharges, and let's see how we can identify these type of partial discharges, or classify this type of partial discharges. So depending on the type of partial discharge, the amount of discharge happens would depend on the we can correlate that into the AC waveform. So if you take AC waveform, whether it is 50 Hertz or 60 Hertz waveform, it would have this positive half cycle and the negative half cycle. So we can correlate the occurrence of partial discharge to this waveform, and we can have this kind of clusters. So these clusters are called PRPD patterns, or phase resolved partial discharge patterns. So these patterns would help to differentiate or distinguish different partial discharges like corona discharges, surface discharges, internal discharges, or floating discharges. So here you can see how different PRPD patterns are correlated to different types of partial discharges. In this first picture, you can see the corona discharge or the negative corona. So this cluster would appear only during the negative half cycle of the AC waveform. There is no cluster during the positive half cycle of the waveform, so that we can easily categorize this kind of PRPD pattern as the negative corona discharge. When it comes to positive and negative, or the positive corona always accompanied by negative corona. So as I said earlier, negative corona starts at the endpoint of the positive corona starts at the endpoint of the negative corona. So whenever there is a positive corona, you would see negative corona as well. So and the negative corona has a higher strength than the positive corona. And in this third PRPD pattern, it is showing the surface discharge. So it would have these clusters both in the positive half cycle, both in the negative half cycle as well as in the positive half cycle as well. So there might be two different strength, or maybe both clusters might have similar or identical characteristics as well, depending on the type of surface discharge. And our fourth partial discharge PRPD pattern is that floating discharge. So the characteristic of floating discharge is that it would have this kind of peaky or the impulsive type of clusters. So it is not necessarily being 2 clusters per half cycle. There might be 3 or higher number of clusters depending on the type of floating discharge. So as summary, based on the PRPD pattern, we can categorize them into different types of partial discharge. So when we use acoustic cameras to detect partial discharges, so we can correlate them to this AC waveform, and then we can differentiate or distinguish what kind of partial discharge is this. Okay, so let's go to practical examples. So here we have this glass insulator string in a high voltage switchgear. So, and we have detected a partial discharge at the high voltage end of this string. And the camera analytics shows this PRPD pattern here, and it gives directly it as a surface partial discharge based on this PRPD pattern. You can see there are clusters both in the positive half cycle as well as in the negative half cycle. So this kind of glass insulators would develop surface discharge because of the contaminations, as I said earlier, maybe due to dust, salt, together with moisture. So when we keep this unattended, or when we don't take any remedial action, over a long time it might goes to surface tracking level. So as you can see from the big picture at the bottom, so this is the glass insulator string that is being removed from exact location, and you can clearly see this surface tracking was initiated there, so that there is carbonized path that is being initiated. So over time that would lead to flashover as well. So therefore it is very much important to detect this kind of surface partial discharges at their beginning or during the routine inspections and take remedial actions. For example, we can wash these insulator strings so that this whatever the contamination should be removed and surface discharges would not be occurring in the prolonged time. And then in our second case study, we have this surge arrestor in this high voltage substation. So in this case, the partial discharge is happening not from the high voltage end, but from the intermediate and the earth potential level as well. So this is a kind of thing that can happen in surge arrestor kind of equipments because of this voltage or the electrical field stress gradient. So that would caused by the leakage current most often, which is due to again this contamination of this external surface of this surge arrestor. So usually these surge arrestors are equipped with this kind of leakage current meters so that we can cross-check with this leakage current meter whether there is a leakage current, or if it is higher than the recommended level, it is always recommended to, for example, washing this surface and whatever the remedial action they can take. So here this snapshot is showing these two locations. That is very important. So both of the locations that is one of the feature of this kind of acoustic cameras. It would not only show the highest sound source but also show the other sound sources as well. So you can have this kind of modes in these cameras, so single sound source as well as multi sound source modes, so that from the single frame you can analyze or you can detect different sound source. Okay, in our third example, here we have a similar substation, air insulated outdoor substation, and here again we are detecting some kind of partial discharge in this insulator string high voltage end, but this time the PRPD pattern suggests it as a corona discharge, particularly negative corona. So you can see in the PRPD pattern, we have only one peak. We don't have another peak in the second half cycle. So mostly this suggests the type of partial discharge by this PRPD pattern as corona discharge. And as we know, corona discharge is the discharge into air. So usually it is a harmless phenomenon and non-phenomenon. It wouldn't cause that much trouble in this kind of installations. But there are types of insulators, for example, polymer insulators, that might get deteriorating or the detrimental effect by this corona discharge because of the production of ozone and UV that would erode the surface of polymer insulator. So there are that kind of cases, but in general, corona discharges are harmless unless you are not worried about this hissing sound and this radio frequency interferences and these kind of things. Usually corona is harmless and no action would be needed. Okay, let's go to the case study number 4. In this case, generator state a PD offline. So the generator is not in working condition in this case. So the rotor is being extracted and the generator stator is being tested with offline partial discharge test, usually with high voltage AC. So in that case also we can use this kind of acoustic cameras to detect partial discharges, for example, on this stator bars. So in this case, the camera is locating a partial discharge on the slot exit around the area of slot exit, and the PRPD pattern suggests it as a surface discharge. So usually this kind of discharges happens because of the damages of or the deterioration of the winding insulation. Particularly in this area, we have this stress grading material insulation, so that might get damaged as well. So it is often recommended to do a visual inspection if you detect this kind of thing during offline test, so that we can see whether there are damages or white powders are accumulated on this insulation, so that we can take remedial actions, we can repair the damages if we found. So this is also an important example because acoustic cameras can be used not only in online partial discharge detection, but also in this kind of offline tests as well. Okay, so we have discussed for case studies and partial discharge application in detail, and now it is good time to move into our second application, which is gas leak detection. So pressurized gases. So these are being used in industries. For example, as compressed air or other type of gases are being used as pressurized gases for various work, various applications. And this pressurized gas might get leaked into the external atmosphere. So in that case, this leak could produce a turbulence in the atmosphere, and this turbulence would create ultrasonic or ultrasound signals that would aid this kind of equipment or these ultrasound cameras to detect these leaks. So this is kind of a straightforward application, I would say, compared to the partial discharge, because in partial discharge case, we have these PRPD patterns, and it will be tricky to differentiate these things, but this gas leak detection is kind of straightforward in that sense. But the tricky thing here is that, so if you compare these two applications, partial discharge detection and the gas leak detection, normally we detect partial discharges in silent environments. We don't have, in general, we don't have that much of noise in these outdoor air insulated substations. But in contrast, here we try to detect gas leaks in noisy environments, noisy industrial environments, for example, power plants or production facilities. So there are 80 to 90 decibel level of sound, background noise. So, but here you can see in this graph, so its x-axis is the frequency and y-axis is the sound pressure level in decibel. So this orange color graph is showing the background noise, while this blue color graph is showing the air leak noise. So if you take this background noise, it is dominating in the low frequency range. In other words, in audible range. That's why we hear a lot of audible noise in this kind of environments. But when it comes to ultrasound level, this kind of gas leaks would dominate than the industrial noise. So we can use this feature to detect ultrasound noise even in noisy environments, because if you filter out this low frequency, for example, with high pass filter, or by using ultrasound camera itself, because these ultrasound cameras operates beyond 20 kilohertz. For example, from 20 kilohertz to 130 kilohertz, that's the typical region we use these kind of ultrasound cameras. So in these regions, the air leak would dominate over the background noise. So even with this noisy environment, we can effectively detect this kind of small air leaks. Even though we can't hear the leak sound to our ears, these ultrasound cameras can pick up these leaks effectively. There are other types of sound sources, for example, electronic noises that is being emitted by electronic sound sources like switching frequencies. But these cameras have inbuilt filters for these sound sources as well, because these sound sources are concentrated into very narrow band frequencies. For example, 40 kilohertz, 80 kilohertz, like monotone signals. So these peaky signals are also being removed by these ultrasound cameras. So those would not affected for this detection as well. So these cameras not only detect and localize this leak source, but also they can estimate the leak size based on the sound pressure level or the decibel level. So these cameras usually have inbuilt analytics to give you the leak size estimation, and given that, user can give some of the input parameters like cost parameters. It can give annual cost as well, the cost of the leak as well. And also it can automatically detect the distance to the leak as well. So in this case, you can see it automatically detects as 3 meters to the distance. Thanks to this beam forming algorithm, it can detect the leak, the distance to the leak source as well. So these are the useful outputs of the ultrasound cameras when it comes to leaks source detection in industrial environments. So we can have a look on some of the case studies for the leak detection application as well. So in this case study, we have this generator hydrogen leak detection. So these are the large generators which are being used in, for example, in coal power plants. So these generators are being cooled by using hydrogen. So inside this generator, there is pressurized hydrogen, usually pressurized up to 3 bar or 0.3 megapascal. So leaks from this leaks to the outside environment is posing a safety risk, as well as it is some hydrogen wastage. Generation of hydrogen would incur cost. So it is very much important to detect these leaks both in the safety point of view as well as cost point of view as well. So if you happen to be in this kind of environment, you would know how much noisy this kind of environment is because of the noise from these large turbines and generators. So often it is more than 85 decibel. But as I explained earlier, this kind of small hydrogen leaks would generate ultrasound that would have dominance over this background noise in the high frequency ranges. So in this case, the camera has been able to effectively locate this leak point from the one of the bolt. So they have been using this soap water to validate this leak. So when they spray soap water on this bolt, so it would form these bubbles, air bubbles, or the hydrogen bubbles in this case. So they can validate this leak. So in this case, they are being inspected by, the leak is being inspected by like 10 meters away. So it would provide a safe distance and to inspect this kind of explosive gas leaks, and also it is very quick and efficient as well. Okay, so in our second case study here, we have a vacuum leak detection in paper industry. So yeah, so this inspection was done by me actually. So this is quite a challenging application even compared to the previous one, because in the previous application we had 3 bar pressure, but here we have only 0.1 bar pressure. So it is a very low or the very tiny leak in this case, and this is called rotating disc filter in paper industry. So inside this filter there is a vacuum environment of negative 0.1 bar. So whenever there is tiny cracks on these filters, the vacuums would be started to leak, of course into the inward direction, but it would produce turbulence and thereby ultrasound, so that camera can be used to detect these leaks. So this is in very low vacuum pressure, as well as this is rotating as well when we are detecting. So it is a bit tricky to detect this kind of very small leaks. The environment is noisy and the disc itself is rotating. So I had to play a little bit with the frequencies in this case, because most of these cameras have the facility to user to define this frequency range, in which frequency range you want to measure. So the user can do kind of trial and error to detect this kind of challenging applications. Yeah, it is very important to detect this kind of leaks at its early stage, otherwise it would cause to significant vacuum drop, thereby potentially causing forced outage and production losses. So whenever if the maintenance engineers or the technicians can detect these kind of small leaks at very early stage, they have good time to plan their outages and take remedial actions. Okay, so we have done with the 2 case studies in leak detection, and now we can move into our next section, which is again a leak detection, but in a different environment, so-called hazardous environment. So there are industrial applications which are categorized as hazardous environments. For example, oil and gas industries, hydrogen generation and storage plants, chemical and petrochemical plants, so and so, like mining applications. So those environments or those applications are being classified as hazardous environments. So we can't use normal electronic devices within those premises. So they have these strict rules and regulations, of course, when it comes to, for example, detecting leaks. So for that kind of applications, we have EETESC or the IEETESC. Those are the certification bodies that would issue certified devices for this kind of environment. So we can have this kind of specially produced devices for this kind of hazardous or the explosive environments. So these devices are having special features, so that having higher ingress protection levels, as well as they are immune to electrostatic discharges, and users can't remove their batteries on site. So all these protections and interlocks they are within this kind of special acoustic cameras, so that these devices can be used in that kind of environments. Of course, you should consult with the safety officers of these premises. So there are different categorizations, different zones, like zone 1 and zone 2. So they would need different level of explosive protective devices. depending on the environment. Yes, so with that, we can move into our next application, which is the mechanical fault detection. So up to now, we have discussed the partial discharge detection and the leak detection with acoustic cameras. Our third application is the mechanical fault detection. So this is a relatively new field for acoustic cameras, but still having a potential, a good potential to detect mechanical faults, maybe at very early stage, as I said earlier. So mechanical faults such as cracks on bearing races in a race or outer race. So those tiny cracks would produce ultrasounds at their early stage of the failure. So, and if the bearing is kind of open bearing and it is open to environment, there is a possibility to use ultrasound cameras to detect such bearing failures at very early stage. And it is always safe to do this kind of scan. You don't need to touch or go closer to the equipment, rotating equipment, and you can safely do the scan at a distance. And you can quickly do multiple, you can quickly scan multiple bearings within practically no time. So there are different matrices that is being used to define these fault levels in this kind of acoustic cameras. For example, kurtosis and crest factor, those are statistical matrices that is often being used to define how much impulsive this sound wave is. And of course, users can compare different or identical components so that it would give comparison, a good comparison. So if, for example, if one bearing is detecting with higher SPL or higher kurtosis crest factor and the compared to the identical one, so we know this something is wrong with this, the first bearing. So that kind of comparison method also can be used when it comes to mechanical fault detection. So in this case study, we have this coupling over here. So in between this driving motor and the driven pump. So in this case, there is a detection from the ultrasound camera on this coupling, drive coupling, and you can see that it has a crest factor of 10. Usually if the crest factor is more than 6, it is something to be worried about. And you have the SPL level of 53 decibels here. So this has been detected with the ultrasound camera, one of the ultrasound camera, and after few days, this drive chain has been failed. So so this is a very good example. We have a detection, and if we don't, inspect or take further actions, it would lead to a failure. So in this case, it has led to a failure of this drive chain. And this is another way of detecting mechanical faults in, for example, this kind of conveyor system. So if you take this kind of a conveyor system, there are large number of rotating elements or rolling elements. So, but camera is pinpointing on one bearing or one rotating rolling element. So it would this kind of camera can be used to quickly detect the noisy element or the failing element of this kind of large number of elements. So this is another way of detecting potential mechanical faults. Even from the kurtosis and crest factor, you can see here there is something wrong here. And in this case, on-camera analytics also suggests there is a potential fault detected. But even without these matrices, the inspector can directly pinpoint there is something wrong with this element compared to the others. This is also a similar example. In this case, we have this coil belt, and these elements are called impact rollers. There are thousands of these kind of impact rollers in this kind of coil belts, because these coil belts are maybe several kilometers long. So it is not practical to do inspections one by one. But if you use this kind of acoustic camera, you can quickly scan through these belts and identify potential failure points or potential faults. So again, this provides a safe, efficient, and easy method of detecting mechanical or potential mechanical faults. Okay, so now we have discussed all three major applications of acoustic cameras: partial discharge, leaks, and mechanical fault detection. So now we have reached to the final segment of the presentation, which is the analytical tools for post-processing. That means, okay, we can detect whatever the fault by using this kind of cameras, but what we are going to do next, or what we can do with the data. So that is what we are going to discuss here. So most of this kind of camera manufacturers would provide tools if the users want to have further look, or have additional insights on these detections. So users can simply take a photo, we call them as snapshots, whenever they detect abnormal event, partial discharge, leak, or mechanical fault. They can take a photo or snapshot, and it would be saved in the camera, and they can transfer them into this kind of offline software, so that it would provide more insights. So for example, if it is a partial discharge, so in this case, it is being detected a partial discharge in this dry type transformer. So it is being classified as surface discharge, and users can have a further look. So for example, they can input voltage level and the location, so that these tools have automatic recommendations, and it gives a description. In this case, says that it is being said that this is classified as a surface or internal discharge. At this stage, the discharge appears to be moderate strength. It will progress over time and lead to complete insulation breakdown. And it gives recommendation like to do visual inspection, cleaning or polluted surface, repair or replacement of damaged component, like this kind of general recommendations. And it give relative severity. In this case, it is more or less very high severity. And some users want to have a look on the time signal and the Fourier transform or the spectrum, what kind of frequencies does this have, and the PRPD pattern. So all of these kind of things, post-processing things, can be done with this kind of tools whenever user wants. And when it comes to leaks, most of the time users want to report these leak cases, because there are multiple number of leaks that would be detected during one inspection round, so that users can simply take snapshots, then transfer into this tool, and it will produce a report on this inspection round, and that can be forwarded into maintenance manager or whatever the one who is responsible for. So it would provide this safe or the easy facility for reporting this kind of leaks. So in this example, it gives what is the estimated leak size, estimated cost, and even this greenhouse gas emissions, how much of greenhouse gas emissions that can be reduced by fixing this leak. So that kind of data we can generate with this by using this kind of tool, offline tools. So when it comes to mechanical faults, we can again upload this file to this and open by using this tool, and we can have a look. Some engineers want to have a look on the frequency components of this sound wave. So for example, in this case, we have a 3 kilohertz frequency and as well as a harmonic of 6 at 6 kilohertz. So then these engineers can relate these frequencies into different characteristic frequencies of this element. For example, in this case, this is an induction motor. So induction motors might generate these rotor bar defects. Those might have specific frequencies. Then engineers can correlate these frequencies into those frequencies and check whether what kind of defect or the fault is there. They can predict these things. So these are kind of advanced things that some of the users want to have a look, but in general, we can use ultrasound cameras, or maybe even an average user can use this kind of ultrasound cameras to detect partial discharges, air leaks, and mechanical faults. And they can get deep insight even without doing this kind of further analysis. So I would say this kind of further analysis are supplementary. It is not mandatory, but if someone wants, they can do with this kind of tools. Okay, so I hope we have done with the presentation and hope you have got a good understanding on the acoustic cameras and its applications and how we can use these acoustic cameras in industrial condition monitoring. So it is now time to have the Q&A session if there are questions arise during the presentation.
Yeah.
Yeah.
Thank you. Thank you, Engineer Manraj. It was a really fruitful session. I think it is useful not only for electrical engineers, it's actually for mechanical engineers, process engineers, production engineers. It is really useful. So thank you again. Right, it's now time to the Q&A session. So Mr. Harsh Kumar Suraraj has raised his hand. So now you can, I think, unmute yourself.
Yeah. Hello, can you hear me?
Yes.
Yeah, we can hear you.
Yeah. Thank you very much. This was a very interesting and very useful presentation. Fantastic. I had a small question in this at the slide mechanical fault detection. It was a rotating machine, and you had a one single point as a detective point. How could it in the camera? How could it happen? If you can go back to the slide where the mechanical fault detection is.
Let me share the presentation again. I think you are referring to this image.
One moment. Not this one, the previous one. This one, yeah. Now this is, it's not the rotating part, isn't it? Okay.
So this is the.
It's not a rotating part, isn't
it? This is a bearing housing, I would say.
Bearing housing. Okay. Thank you very much. Yeah.
So these are these kind of open bearings. So if there is a fault in the bearing, it might generate ultrasound and it can be detected with airborne ultrasound. But there are applications that bearings are hidden inside. So in those cases, it is not practical to use this kind of ultrasound cameras to detect bearing faults. For example, journal bearings, we can't. Definitely, journal bearings would not produce ultrasound as well because those are sliding on these oil layers.
Yeah.
There are sealed bearings which are enclosed inside motors. So in those cases, it is not practical to use airborne ultrasound. But this kind of open bearings, which is open to the environment, I would say. So in some cases, this can be detected. Yeah.
Yeah, and those are static, is it? They're not moving.
Actually, the bearing is rotating, but this outer, I mean, this is the bearing housing
Small.
is stationary.
Yeah, yeah. So this is a fault of in the housing, is it?
You can't exactly say whether I mean, it is not that much practical to differentiate whether it is from housing or the bearing inner race or outer race or from where, because you can't have that much of spatial resolution with this kind of camera. So that's why I told earlier as well, if you want to have this kind of detections, it is best to use comparison. So there is another bearing in the other side, so you can get this SPL level, kurtosis and respect or whatever thing, and it can be compared with a similar bearing. That's the best way to detect fault for this kind of applications, because this kind of noise can be normal as well. From one single detection, we can't exactly say whether it is a fault or not.
Yeah, okay. Thank you very much. Thank you.
Okay, no worries.
Thank you very much, Mr. Harshkumar. So we can wait for another few minutes if the participants have any questions.
Hi, thank you very much for your presentation. Actually, I have a small question. You mentioned about offline PD, right? Offline partial discharge. So what is the main devices that you use for offline PD? Because currently in Sri Lanka, we don't use offline PD as much in the utility sector. So what are the main devices that is it like damping AC technology, which is introduced by figure?
Yeah, in my knowledge, in Sri Lanka also you should use offline PD detection, for example, in this kind of large generators. So what I know is they use this corona probe method. So what they do is that they apply high voltage onto this stator and they use a probe so that can detect this electromagnetic emissions or radio frequency emissions from these tiny discharges. So they move this probe along this stator bars and detect if there are tiny partial discharges. So that is called corona probe method. In addition to that, normally this coupling capacitor, that's the standard method that is being used for partial discharge detection according to this IEC, whatever 20270 standard. What it suggests is that to use this coupling capacitor based detection, but I'm not too sure about how in which extent in Sri Lanka, and yeah, it is being used. Maybe someone who has some
yeah, actually I was referring to mainly the power transformers. Do you have any case studies or experience related to damping AC technology?
No, honestly, I don't have. Yeah, I am dealing more or less with this ultrasound technologies, especially with ultrasound cameras, not with partial discharge in general.
Right. Thank you very much.
Okay, thank you, Mr. Chandula. So we have a question in our chat box. Mr. Dilip Daulagal has raised a question. Mr. Manla, can you go through it, or is it okay if I read it?
Okay, you have any experience with detecting corona discharge within the slot person of this data binding using acoustic cameras. Ever tried anything of this nature? Any success? I have not done personally this kind of detection, but I know there are so many slot discharge detections have been successfully done from our customers, by our customers. Of course, I can't expose these cases who has done this, but I know there are so many cases that they have successfully detected this slot discharges. Yeah, both slot discharges as well as this end-winding corona as well. But as I said earlier, this is during the offline testing, not during the online. No. Online we can't do anything with this acoustic cameras. But offline, yes, you can. As I know, Dilip, you are dealing with this asset monitoring of CEB, so you can try with this kind of acoustic cameras whenever you are doing this kind of, for example, corona probe test. You can try in parallel to corona probe test. You can try with this kind of acoustic cameras to locate these discharges. And on the acoustic, if you are, the advantage of using acoustic camera is that not only detect or locate the partial discharge, it would say you whether it is corona or surface. So that would give more insights on the partial discharge. I suspect this corona probe would not provide that detail for you.
Yeah, okay, thank you. Mr. Mohan, another question is there in the chat box from Mr. Ashan Hapwarachi.
Yes, there are acoustic cameras which have different frequency ranges such as 2 to 40 to 200. What is different between them? Okay, so yeah, you are correct. There are different acoustic cameras. Basically, they operate from 2 kilo. The minimum is 2 kilohertz. The maximum is 130. So if you take this kind of camera in here with me, so I'm not sure you can see the lowest is 2 kilohertz and the maximum is 130, and the users can select in which frequency that they want to operate. So the difference you are asking, so it is like that. So these kind of high frequency ultrasound would attenuate more quickly over the distance. As a thumb rule, higher the distance, higher the quicker the attenuation, higher the frequency, quicker the attenuation. So if you go to like 100 kilohertz, you have to be really close to the source to detect ultrasound. But the advantage is, if you are detecting with 100 kilohertz, you can remove all the background noises, most of the background noises. But the disadvantage is you have to be really close. So that's why I explained during this vacuum leak detection of this rotating disc filter. So I had to do some trial and error with these frequencies to check at which frequency I can dominate over the background noise. But it is kind of a trade-off between the frequency, distance, and the background noise. So there is no really one-way answer, but if you can go closer, you can go to higher frequencies. Then you can avoid most of the background noise. But if you can't really go to closer, maybe for practical reasons, then you can't detect, of course, in 100 kilohertz, then you have to lower your frequency. So it is kind of a trade-off. So when it comes to 130 kind of frequencies, most of the manufacturers put these things because of their specifications, to increase their specifications, but practically these very high frequencies are not that much effective because you can't, the frequencies get attenuated in the air very quickly, so that these camera microphones would not receive at all these very high frequencies. So that is the difference. So most of these cameras, users do not need to actually select frequency. They can use this kind of auto frequency option. So they can put into auto, and then this camera can automatically adjust the frequency depending on the background noise. So yeah, auto frequency can be used, but when it comes to really tricky applications, maybe we might need to play with manual frequency. I hope I answer your question at least some extent here.
Yeah, thank you, Engineer Manu. I think yeah, he got the answer.
Yes, go ahead.
Thank you very much, Mr. Malula, for your nice presentation. I would have one question that we recently got in our faculty that hyperspectral camera. So that is for our mainly for the research works, but that is, can we use this kind of purpose for that camera also? Is it possible to use that one
Shall we know
for?
what does it mean by hyperspectral camera? I have never gone through this kind of cameras. Is it ultrasound camera or any other technology?
No, I use I think it have a lens and it getting the images, and then they get the frequency components from these different image parts. I'm also not an expert in that area, but I heard that they got a hyperspectral camera, so that's why I'm just want to clarify if there are any possibility
So
with
I
that one.
suspect it as a thermal imager or any, if it is having a lens, maybe it is a thermal imager or maybe a UV camera. So
Not thermal image actually. We
is it a
can
UV camera then, ultraviolet camera?
yeah, something like that. Yes.
Okay, so ultraviolet is also a technology that can be used to, for example, detect partial discharges. So whenever there is a partial discharge event, it produces ultraviolet. So we can use ultraviolet cameras, of course, to detect. So those are electromagnetic waves, not mechanical waves like ultrasound. So yeah, ultraviolet cameras are being used in, especially in this outdoor air insulated switches, high voltage switches, and transmission lines. And those can be mounted on drones, so that drones can fly over these transmission lines and check insulators whether there is ultraviolet emissions from these insulators. So it would suggest a possible partial discharges. But the disadvantage of using ultraviolet cameras over ultrasound camera is that ultraviolet cameras can't classify the type of partial discharge, whether it is corona or surface, because this ultrasound cameras has that facility thanks to this beamforming technology, so it can correlate with the PRPD patterns. So it is a
Okay.
different
Thank you.
technology, different technology to
Thank you.
detect partial discharges, but not for, of course, leak detection and mechanical detections.
Yeah, sure.
Right. Thank you very much, Engineer Manu. I think it's now 8. It's close to now 8:30. So I think participants are not having any other questions. No, Mr. Pool has raised his hand. So
yeah. Can you correct this? Why we do inspection using ultrasonic in shipbuilding, structural welding sort of things. So those things, I think, the acoustic camera technology can be used or cannot be used.
Okay, so what you do is you produce ultrasound and then you do whatever the structural thing. So here we are using a passive kind of thing. So we use this ultrasound produced by some, for example, partial discharge, leak, or mechanical. So these are two different things. So here we are
Yes.
using receiver. What we are using is a transmitter. That's what I understand. These are two different applications.
But if it is pneumatic pressure loaded, then we can use this, no? Hydro testing sort of things.
I'm not too sure about the application. So if you want to, of course, detect pneumatic.
We pump air in the containment.
Okay. Then what you do?
If there is a leak, it will produce ultrasound, no?
Okay. Yeah. Maybe you can try. Yeah. I'm not. I have never gone through this kind of application, but of course, if you have pressurized air and if there is a leak, it will produce ultrasound. Depending on the size of if it is too tiny leak like hair cracks, I'm not too sure it can be detected. But practical, if there is a practically, if it is producing enough ultrasound, and of course, it is something that has to be tested with actual setup. Otherwise, I can't directly answer whether it can be detected or not.
Okay, thank you so much for the nice presentation, Manula.
Of course, no worries.
Right. There are no questions in chat box, so we can, if any participant want, we can give another one more chance because it's close to 8:30 now. Right. Seems like there are no any other questions. So we can go to the next. Sorry. Okay. Not a question. Right. Okay. Thank you very much. Now we can go for the next item of our agenda. So I could invite our second. Yeah. Dr. Geeti, are you hearing us?
Oh,
Yes,
yeah. Is it, am I audible?
Yes.
Okay. Good evening, ladies and gentlemen. We have concluded today's webinar. It is my privilege to propose the vote of thanks. First and foremost, I extend our sincere appreciation to our distinguished resource person, Child Engineer Manula Malraj, for delivering an insightful and technical rich presentation and for sharing his valuable industry experience with us. I would like to respectfully thank the President of Institute of Engineers Sri Lanka, Engineer Kosala Kamburagania, for his continued guidance and support to EETES activities. My sincere thank also goes to Chairman of EETESC, Engineer Viraj Mutugala, for leadership and commitment in steering this webinar to success. I gratefully acknowledge the organizing team, including all the members of the EETESC Executive Committee, for their dedication and hard work behind the scene. Our thanks are also extended to the IESS CEO, Engineer Neil Abesekar, and the IESS Secretariat for their continuous administrative and technical support. I also like to appreciate Engineer Dushant for skillfully moderating the session and facilitating the discussion. Finally, I thank all the participants for your active participation and engagement, which truly made this session meaningful. Thank you all, and we look forward to welcome you to our future EETESC events. Have a pleasant evening. Thank you.
Thank you, Dr. Geet. So now we are going to wrap up the session. So thanks again, Engineer Manu Maharaj, for your valuable time. And thank you all for the participation. So we'll close the session. So we'll meet again in another session with an interesting topic. Thank you. Good night.